Hello, we are starting a new topic. We are now working with transistors. And the first transistor that we are going to study is the BJT transistor, the bipolar junction transistor. Bipolar, two polarities. We have two charge carriers working here, free electrons and holes, meaning electrons conducting in the valence band. So as we have done before, anytime that we have a new device, to understand it, we want to look at the current voltage characteristics, and then we also want to look at the structure and see if we can comprehend the operation in terms of fundamental physical principles. And then we start doing circuit analysis, right? So let's go with the BJT. The BJT is a three-terminal device like other transistors. So far, all our other devices are two-terminal devices. So in this case, we have a base, we have an emitter, and we have a collector. This is the NPN transistor. It's the first one we are going to study. And as I mentioned before, we have a new device. How do we study it? Well, we look at the current voltage characteristics. Once we understand the current voltage characteristics, we can create a model, an equivalent circuit, that is going to simplify the analysis and the design. And with that model, we're able to do DC, circuit analysis, training transistors. We look at then what's going to happen once you have the transistor or that device biased at a particular quiescent point, and we can also come up with an AC model. And then we can do analysis with that device on any circuit. So let's start with first. This is the symbol. Three-terminal device. And so if we wanted to understand it, in this case, it's not just to change one voltage source and see what happens to the current. We need to change two voltage sources, as we have it here. I'm going to do an LTSpice simulation. And we have to do a couple of simulations just to understand this device, because as a three-terminal device, it can operate as a switch, it can operate as an amplifier, it can operate in the active region, in the cutoff region, in the saturation region. So it's going to take us a little bit more time to understand this device. But of course, it is extremely useful, and so it will be well worth it. So let's start with the current voltage characteristics and with an initial model. One thing that we could say is what happens if we change the voltage between the base and the emitter to the currents flowing through the device, right? This is the collector current, this is the emitter current, and this is the base current. And with that simulation to start doing a model, right? What you're going to see is that this device, you can think of it as a voltage control current source, where if you change the voltage between the base and the emitter, or as you change the voltage between the base and the emitter, you control the current through the collector and emitter, okay, terminals. And this is, if we explore what's going on here between the base and emitter, that's like a PN junction. We are going to see when we look at the structure. So what we expect is going to happen is if we change the voltage base emitter, as we change it, and we look at any current, the current in the base, or the current in the emitter, or the current in the collector, is that unless we bias that junction, or before we have 0.6 to 0.7 volts across the base and the emitter, we get no current. We are in cutoff. And then it's going to turn on. That part of the transistor looks like a diode. Okay? Let's see if that's the case. Let's do a simulation here. So what I have is a BJT transistor. I chose one of them. I connected a source between the voltage between the collector and the emitter, 10 volts. I collected a source between the base and the emitter, and I'm going to do a parameter sweep, a source sweep. So the voltage between the base and the emitter is going to go from 0 to 0.5 to 0.8 in increments of 0.01. Let's run it. And so we see here in the x-axis the range of voltages that we simulated, and let's look at the currents. So let's look at the current through the base. Oh, sorry, that's the voltage. So let me get this off. So you can see that the voltage has changed linearly. Based on our simulation. Current entering the base terminal. And there you go. As expected, we get an exponential relationship. We could say that the base current is going to be related, is going to have an exponential relationship, so you have a constant here of proportionality, e to the Bd over Bt. Okay, that's what we are trying to do, some equations as how this works. Now, we're going to see that constant, we will determine it later. Now, what about the other currents, the emitter current, the collector current? Same thing, unless we had a voltage between the base and the emitter, we get no other currents. Now, the collector current and the emitter current are significantly larger than the base current by a factor of beta. So let's go ahead and just plot them here. So this is the collector current, much larger, and the emitter current is going to be very close to the collector current. Now, because it's looking at the current entering the terminal, you are seeing the opposite polarity of that current. So I'm just going to multiply times -1. So you get it there. So that's the emitter current. This is the collector current. Almost identical, as you can see. So what we can see is that this is a device where you could think a simple model will be, I'm going to do a mechanical model. This will be like a valve. Where the voltage between the base and the emitter controls the current in the collector, right? And through the emitter branch. That's one way to think it, right? So you have a voltage control current source. Now, we can think about this device as, therefore, as a transconductance device, meaning we are creating a voltage control current source. And voltage control current sources are of course useful to create current sources, but once you have current sources, you can also create amplifiers. Now let's look at how the voltage at the collector, or between the collector and the emitter, influences the behavior of this device. Right? Well, the things that we're going to see is that if we are to plot the currents, the current at the collector, as a function of the voltage collector emitter, is that it is going to be largely, for very low voltages, say around 0 to 0.2 volts or 0.3 volts, you have a particular relationship, but then it is largely independent of the collector emitter voltage. When we look at the operation, based on the structure, this is going to make more sense. But this is the type of characteristic. This is for a voltage base emitter 1, voltage base emitter 2, etc. So this is how it's going to look. Voltage base emitter 3, meaning the voltage between the base and the emitter is going to control how much current we have, and then it is going to stay constant for different voltages between the collector and the emitter. Let's see if that's the case. So what I have here is a sweep where I am changing the voltage between the collector and the emitter from 0 to 15 volts, and then I'm changing the voltage between the base and the emitter from 0 to 8 volts. So as you can see, in terms of voltages, we are changing it from 0 to 15 volts. We are interested in looking at the currents. So the current here, the collector current, these are the characteristics that we get. So you see that unless we have some voltage between the base and the emitter, we are at cutoff. It doesn't matter how much you change the collector emitter, you get no current. Okay? That's the cutoff region. So the cutoff will be no current, right here, cutoff. Why is that? Because you are operating in this region, not enough voltage between the base and the emitter. The transistor is not turned on. But once you reach the 0.7 volts, now you can be in either of two regions. The active region, which we are going to use for amplifiers, or the saturation region. So the transistor can be in cutoff, active, or saturation, depending on the bias. What is the bias? Well, how we connect the DC sources and what are the voltages that you see between the base and the emitter and the collector and the emitter. We can see that once the base emitter junction is forward bias, meaning we are around more than 0.6 volts, around 0.7, now you have current flow in the collector, in the emitter. So, and what is that collector current or that emitter current? Well, we can see that it is largely independent after a few volts of the collector voltage, collector emitter voltage. We can also see that the current in the collector and the current in the emitter is very close. So let's do it. Actually, let me put here a resistor. No, let's not do that. Okay. So if we were to develop a model, we will say, well, for the active region, for this region here, we'll say the voltage between the base and the emitter needs to be approximately 0.6 to 0.7, meaning we have a base emitter junction bias. And if that's the case, we have that the collector is approximately equal to the emitter current. If you look closely, you will see that the emitter current is slightly higher. Okay? And why is that? Well, if you look at the currents, here you have that the emitter current is equal to the collector current plus the base current. Now, if you do the difference between the two of those, you get the base current. And so you can see that the current entering the base is much smaller. Again, when we go over the structure and how this operates based on the fundamental physical principles, it's going to make total sense. So, voltage base emitter, 0.6 to 0.7 volts. Currents are approximately equal. The emitter is the combination of the two. The difference of the two is the base current, and so that also leads to another model where you can think of a small current in the base. A small current in the base controls a larger current in the collector emitter. Okay, that will be a current control current source or a current amplifier, meaning IC equals beta IB. Okay, where beta is the current amplification factor, HFE in the datasheets. So you can think of this as a current amplification, meaning we can do, and this will be for a base current, and you get a much larger collector current, base current 1, base current 2. We can do that simulation too. And if you wanted to do precise analysis, then we have that IE is equal to IC, which is beta IB, plus IB, or beta plus 1 IB. Okay? So again, we are with this model. Voltage base emitter, approximately 0.6 to 0.7, IE approximately equal to IC, exact analysis IC equals beta IB, IE equals beta plus 1 times IB. Now when we are doing circuit analysis, beta changes so much for the same transistor type in mass production, as well as changes with the collector current, as well as changes with temperature, that this beta and beta plus 1, it is not a good idea to be that precise in your calculations. So I typically will just use this simpler model, and then you simulate. Okay. Also, we need to do circuit design that is as much as possible independent of beta. Let's look at another simulation. In this case, looking at the collector current in terms of changes in the base current as a current amplifier. This is what we have here. So in this case, what I'm changing is, again, the voltage between the collector and the emitter, but I am supplying, sourcing a base current that goes from 1 micro all the way to 1 milli. And what we are going to see is a similar behavior here, right? So we see that a small current at the base, so gives you a larger current in the collector. By how much? By beta. So this is a current amplifier. Small current at the base, large current at the collector. Okay? By a factor of beta. So let's recap. A transistor, a 3-terminal device. Because it has 3 terminals, it's going to have different modes of operation. Okay? It's more complex than a 2-terminal device. It can be cut off. It can be on, so it can be used as a switch. And then, even when it is on, it can be on in different ways, depending on the bias. Think of biasing as programming your transistor, supplying DC voltages between the terminals so it works in a particular region. So, the transistor works differently in this region between 0 to around 200 millivolts or 0.2 volts, right? That's what we are going to call saturation, where it does depend on the collector voltage. Then, in this region, over here, the active region, which we are going to use for amplifiers, right? Once we do the current voltage characteristics to understand the device, and in this case understand that we have to sweep two different voltages, we can start thinking about models, circuit models. And so we already wrote here the models. If we wanted to do an equivalent circuit for this, it will be something like this, right? There are several ways that we can put this in form of a circuit. BJT model is a large signal model. This can be our base. A model is creating an equivalent circuit, which needs to be comprised of resistors, capacitors, inductors, current sources, and voltage sources, which can be independent or dependent. That's it. That's what we can do circuit analysis with. So if you get a new device, a new structure, NPN structure, well, we need to model it with an equivalent circuit. Now, models have different complexity, so the simplest model that we could think is, okay, this is going to be a diode, for which we already have a model as a voltage source between the base and the emitter. That needs to be around 0.7 volts to be biased. And then we have a current source. And this is the collector current. And one model is that the collector current is approximately equal to the emitter current, which is approximately equal to beta times IB, the base current. So this, both, you could think of this as a current amplifier model. The collector current is beta times larger than the base current, what we have here. You can also think of it as a voltage control current source, meaning the voltage between the base emitter controls the current in the collector. And with this, we can already start doing circuit analysis. You have a lot of examples in the other videos on how to do this. Thank you.